Okay, welcome everyone to the week 5 tutorial. I think I'll just wait for maybe one more minute for people to come in. Okay, participants is 24. How many am I expecting? I'm not sure. I think around 24 or 25 people because there are additional people as well. Okay, then I think I'll wait for one more participant of 403.
Yo, Chris.
Yo, what's up?
Have you opened the archipelago questions yet?
Oh, thanks for reminding me. I haven't opened it.
Yeah, no problem, man.
Because the thing is, right, archipelago kind of like the session automatically opens, but I have to manually switch on the question. So I switched them on. If you have answer, you can bold it there. Yeah,
Cool.
Thanks for reminding me. Yeah.
No problem.
Okay, cool. Okay, nice. So let's begin. This week, we'll be talking about analyzing randomized algorithms, and you guys will have gone through, hopefully, 2 weeks worth of lectures of randomized algorithms. But if you haven't, don't worry. This tutorial is kind of like independent of the lecture, kind of. Okay, so, I'll just double check I've started recording. Nice, I have. Okay, so this looks like a lot to cover, but they are usually shorter sections, right? So I'll talk a bit like why we want randomization. Then I'll talk about the different concepts like the random variable and geometric distribution. Then afterwards, I'll talk about linearity of expectation, as well as the common example called the coupon collector. The last section is a small additional section I kind of prepared for my tutorials, analyzing using indicator random variables. But I talked to Prof that I mentioned to Prof I'm doing this. Then he told me, oh, can you prepare like an additional sheet for the entire cohort? So, so I kind of like adapted this slide to a note that I'll release later today. Okay. So first off, like why randomization, right? Because sometimes you don't always get the correct answer, or things become not deterministic, right? But randomization is nice because we get to guard against worst cases. So for example, when you are using quicksort, right? A naive, like normal quicksort, deterministic quicksort, you can give like a reverse order input, and then very easily you can make quicksort run in O(n) squared. But if you make some random decisions in your algorithm, this quicksort makes it difficult for some adversary to come up with some input, because even the algorithm doesn't know what it's going to decide, for pivot. Okay, so guarding against worst cases, this is the first thing. Secondly, performance, right? And I think you haven't really seen an example where performance is optimized for randomization, but I've seen randomized algorithms where you can optimize from something exponential time to linear, right? You can imagine 2 power n times m, right? There are two variables, 2 power n times m, it becomes O(n). I thought that was really cool. Okay, next thing, simplicity. Most randomized algorithms are actually very simple. In the words of my previous TA, it's borderline dumb. Like it just flips coin, then okay, I'll make decision based on that coin flip, or I anyhow choose, then something like that. So I took these two examples from a module I'm taking right now. You don't have to understand, of course, what's going on, but you can see like how short the algorithms are. The randomization here in the right side is hash function. HU is a hash. Okay, so it's very short, it's very simple. Okay, but the difficulty in randomized algorithm is in analyzing it. That's why this entire tutorial is kind of like on analyzing randomized algorithms. So finally, we also want to do better. In the first week of lecture, you might have seen examples where you try to have deterministic lower bounds, right? Some algorithms cannot do better than, say, big omega of n. Okay, by allowing some randomization, at a bit of like error, if you allow, okay, I allow that the answer is off by 1 or off by some percent. If you allow that error, right, you can actually beat this lower bound. Sometimes it's independent of n. Maybe it's dependent on the error. Like, for example, this algorithm actually depends on the error epsilon here, but never mind if you don't understand. The point is that you can beat the lower bound. Okay, so this is a quick motivation of like why we are interested so much in randomization, why Prof Arnav has an entire module on randomized algorithms. Okay, so first question, worst cases. Okay, now in this example, right, like I want to select some of you. I'm sure some of you have not prepared for questions in class. Okay, so let's pretend I'm evil today. Okay, hopefully I'm not as evil usually, right? So I want to select K of you, K students. Okay, then I consider this a worst case. If, for example, I choose K of you, and then turns out that the K of you are the ones who have prepared, and you are the only ones who have prepared. So it's kind of like fooling me, you know, like I think that, oh, it turns out the entire cohort, entire class has already done their homework or has done their work. But in reality, it's only the people that I chose. Some reason, like you are the only ones who have done, the rest haven't done. So the rest of you are safe. Okay, so suppose, right, I tell you how I'm going to choose. I tell you my algorithm to choose you guys. Okay, can you guys like cooperatively force a worst case to happen? Okay, so for example, maybe I chose like here Naruto and Kirito. Like, hey, can you answer the questions? Then two of them say, okay, I can because they prepared. Then turns out only two of them have done the work. The rest haven't. And it seems like only two of them, it seems like the whole class has because I'm only asking K of them. Is the question clear? Okay, give me a cross if it's not clear. I'll repeat. Take a thumbs up if it's okay. Yep. Okay, question is clear. So I think it's a simple yes or no question. So give it a bit of thought and answer an archipelago while I oopsie. Okay. Yep. So let me just go on to archipelago real quick. Okay, I see mixed responses. People say yes, people say no. Quite balanced, actually. So who will win? Yes or no? 7, 6. Okay, nice. Okay, so I think we can proceed. It's okay if some of you haven't answered yet. Just fill in. It's quite close. It's actually about 50-50. But surprisingly, the answer is actually no, right? Because I can come up with a randomized algorithms. Okay, the first time I saw this, like in my own tutorial when I was a student, I was also bamboozled. I thought the answer was yes. But the thing is, I just say I will design an algorithm, but I say that this algorithm is randomized. So even I don't know who I will eventually choose. Like my algorithm will decide for me by the random choices. So I choose K of you randomly. Okay. Even I don't know, even if you know that this is my algorithm, you don't have enough information about who will be chosen. Unless like you know what the random numbers are gonna be, of course. Then in that case, maybe it's not as random as it is claiming to be. Okay. So the idea here is that because the algorithm makes use of randomness to make decisions, even you guys who know the algorithm cannot find out a way to force this worst case, cannot cooperatively find out like who I am going to choose, because again, it's random, right? Does this explanation make sense? Any questions about this? Okay, so this is, I hope, a pretty simple argument, right? If you have any questions, feel free to ask later, then I'll move on. Okay, so next thing, okay, switch gears a bit. This is a kind of like a new concept maybe, or like something that I introduced in the class. Okay, so a random variable. Some of you maybe have done stats, ST2334 or ST2131 may have seen random variables, but name is a bit misleading because random variable is kind of like a function. It maps a sample space to a real number. So for example, right, maybe a random variable X is a number of hits in 2 coin flips, for example. Okay, so the sample space is all the possible combinations, HH, HT, TH, TT. Okay, then this random variable is kind of like this black box, this function, right? You tell it, okay, this is the thing that happened, HH happened. So can you tell me the number of hits in 2 flips? So it is, okay, the number is 2. Okay, so this is kind of like the function idea. You give it some input, then it gives some output. It maps something. Okay, and mathematically, you might express it like this: x equals to 2. WP is with probability. So you'll see this occasionally with probability a quarter, 1 with probability half, because it's either H tails or tails and hits. Okay, so sometimes you also write it in this way: probability of x, right? The random variable like spewing out the number 2 equals to a quarter, right? This is the HH case. So these are just different representations. Okay. Now, next thing I want to talk about related to this Bernoulli trial, right? Bernoulli trial is kind of like you do an experiment, you try something, and then you have a probability P of success or Q of failure. You either succeed or you fail. Just imagine in this scenario, when you do an experiment, either you succeed or you fail. No middle ground. Okay, just to extreme success or failure. So you can think of it like something like a generalized coin flip, because a coin flip is half, probability half and half. But here is either you land hits with probability P or Q or fail otherwise. Okay, 1 minus P. Or you can think of it as a bias coin, maybe, right? The point is it's either like a success or a failure. So here's another example, right? You can define success in any way you want. For example, success for you might be getting a 6 when you roll a die. Okay? And failure is everything else. If you roll a 1, 2, 3, 4, 5, that's a failure for you. Okay? So this is a Bernoulli trial with probability P of 1/6 for success and 5/6 for failure. Okay? Hopefully understandable so far, because I think it overlaps quite a bit with, say, your high school probability also. Okay? Now, geometric distribution. If you haven't done SD2334, this might be new to you. Okay? Suppose we have sequence of independent Bernoulli trials. So this is you doing the experiment, the Bernoulli trial all over, like repeatedly. Okay, like flip coin repeatedly, for example. Each of them have probability P of success. So in the case of coin flips, there will be half. And each trial, so you're doing the same trial over and over and over again. Okay, so it's the same trial, they must have the same probability. Now, this random variable I will define, right, counts the number of trials you need to obtain success for the first time. It's kind of like saying, keep trying until you get it. If you fail, try again. If you fail, try again. If you fail, try again until you succeed for the first time ever. Then you stop. Then after you stop, you see, okay, how many times do I need to try before I succeed? Okay, this is the intuition of a geometric distribution. Okay, so X follows this geometric distribution, and this is how it's kind of like denoted. Probability of X equals to K equals to, this is like saying you are failing. For you to try, if you needed K tries, you have to fail K minus 1 times first, and then succeed finally. Okay, succeed on the Kth try for the first time means that you failed K minus 1 time, then finally you succeed. For example, K equals to 5. Then that means you must have failed, say for example, a coin flip 4 times, fail the coin flip, fail the coin flip, fail the coin flip, fail the coin flip. Then finally you succeed with probability P. Okay, so this is how geometric distribution is defined. The other one, I won't go through like the derivation of the expectation, but just remember, it's pretty simple to remember, just 1 over P. Okay, and the intuition I like to think about is like, for example, you roll a dice, right? You're expecting success is getting a, say for example, a 5. Okay, out of like you roll it, you have to roll it 6 times. Then probably you expect only like the final one, maybe for it to be like to come up 5, you know, like out of 6 dice roll, you expect maybe the 6th one if you are pessimistic or something. Okay, so intuition wise, that is how I like to think about it. Might not make sense to some people, but either way, just remember this. I don't think it's that hard to remember that it's 1 over P. Okay, hopefully that wasn't too fast. But if there are 2 things to remember here, geometric distribution is you keep trying until you succeed, and the expectation is 1 over P, 1 over the probability of success. Okay, so for example, okay, here is me going through some examples, right? So for example, coin flips, right? Probability of success is half. Then expectation for the number of coin flips to reach hit for the first time is 1 divided by half, which is 2. Okay, simple enough. Then as I mentioned earlier, say I'm rolling a dice, then I want to get 2 for the first time ever. So what is the expected value of this random variable? Okay, number of trials I need before I roll 2 for the first time. So similarly, the success probability is 1 over 6, and the expectation of that random variable is 1 over 6, which is 6. Okay, hopefully this example is simple enough. Now, going on to the tutorial questions, or before that, any questions? Was that too fast? I feel that I was going a bit on the faster side just now, but I think the concept is relatively simple. Okay. Next question in tutorial, then I'll move on, is now I really want to find people who have not prepared. Okay, for example, I'm committed to find one of you guys who have not prepared. Okay, let's say, right, so what I do is I'll keep asking questions, and for some reason I'll also choose with replacement, like choose one of you guys with replacement. So once maybe I've asked Naruto for like his answer, then I realize, oh, he has answered the question, and he knows, he has prepared. Then I can choose randomly again, still considering Naruto, so I'll choose him possibly again. So for some reason, that is my algorithm. But I will keep trying until I find one of you who have not prepared. Okay, so let's say we have N students in total, and K students have not prepared. In expectation, how many questions do I need to prepare? How many questions do I need to ask before I find the first student who have not prepared? For example, let's say these 3 people have not prepared. Okay, so they have not prepared, and I want to identify one of them, right? And I keep trying from all these 8 people until I find one of them. Okay, hopefully question context is simple enough. So give you a bit of time to fill in archipelago. So it's hopefully you can know what concept to apply, then try to do the math. Okay, what's this? 419. Okay, nice. Okay, so I've got a question. Will it be more efficient if we don't do replacement? So I think the question is on like, how come I am sampling with replacement here? Yeah, definitely if I don't do without replacement, then eventually I will find one of you. But for the purpose of the question, for the purpose of making it similar to, spoiler alert, geometric distribution, this is how the question is framed. Okay, does it answer your question? Okay, nice. I received. Yep. Okay, so just for the purpose of the question, ISN, what's ISN? Okay, so never mind. People have answered. So okay, type wrong. So right. So hopefully you see this is exactly a geometric distribution. The somewhat like exercise here is for you to find the probability P and then calculating the expectation. So remember, K students have not prepared. So if my success is finding the student who have not prepared, so this probability of finding them is K for those who have not prepared over N. Oh, I realized I flipped the color. Oops. So the color should be the other way around. So K over N. Okay. So K over N. Then, okay, because I think some of you answered K over N in the answer. The thing is, right, I'm finding the expectation for me to identify one of you who have not prepared. So the expectation by the formula, you have to kind of like take the reciprocal 1 over it, 1 over K over N, you get N over K. Okay, so this is hopefully everyone gets this because most of you already answered N over K. So I think that's good. Okay, so let's go on to linearity of expectation. And this is probably something you have seen in lecture, something you have heard before, hopefully, where this is just telling you that if you have the sum of 2 random variables, X and Y, excuse me, take the expectation of their sum, it is equal to the expectation of their individual random variables. Okay, so let's go through example in a bit. But I want you guys to remember this well, because like I use linearity of expectation almost everywhere for randomized analysis. So even like in one of the modules I'm doing now, for the past 5 weeks, all I've been doing is linearity of expectations. Okay, so it's a very simple thing. Very you probably, if you see EX plus Y, you're very tempted to distribute the E, like distribute the expectation, right? Luckily, it works for linearity of because of linearity of expectations. So I want you to remember this well. If you see anything like this, right, think of linearity of expectation. Okay, so again, new concept now. New concept. Something that we want to introduce in this tutorial is a harmonic series. Maybe you have seen it in one of the extra sheets, but a harmonic series is that essentially you take 1 plus 1 over 2 plus 1 over 3. Notice that the denominator increases 1 by 1. Okay? This thing, smart people have proven that it's equals to ln of n plus some constant. Okay? And for the purpose of the module, for the purpose of, say, we algorithm people, we only care that it's theta of log n. And remember, it's log because we can change the base anyway. Okay? So we care that this harmonic series is bounded but from above and below by log n, theta log n. Okay? So just kind of like remember this, and this n is actually substitutable, you know, like if you have other parameters like n plus 1, then this will be like log of n plus 1, something like that. Okay? For finite number, of course. Okay? You can try proving this. I think you can either use calculus or you can observe things about area under the graph to estimate things. This is a way to prove harmonic series. Okay, so now, having said that, right, I want to introduce some like pattern, because when I'm doing randomized analysis, I notice it's always kind of following this rough idea of pattern. Okay, first of all, usually when we want to count something, count the number of occurrences of something, we make it a random variable. Okay, and we'll go through an example soon. So for example, random variable x. Okay, we want to count this and we want to know the expectation, what the count is. Next, we express this as the sum of random variables. Okay, so count how many things. We try to decompose it to individual random variables. Okay, I know this is vague, but hopefully an example later will clear this up. So express it as sum of random variables. And then what you want to do, right, calculate the relevant probability of x1, x2, x, and all the way to xn. Okay, relevant meaning like maybe probability of success in the case of Bernoulli trials. Okay, calculate their relevant probability, and using the relevant probability, calculate their expectation. Okay, calculate their expectation, because if you have all the probabilities that you need and you know what the values they take, you can calculate that expectation by definition. Okay, then finally, use linearity of expectation on E of x. Use it on E of x, then you can kind of like distribute the expectation to x1, x2, all the way to xn. So it can be E of x1, E of x2, all the way to E of xn. Okay, then because you have calculated their individual expectation, you add them up. Okay, so keep this pattern in mind. I will show it later in the slides as well as we go through an example. I'll go on, even though maybe you have some questions, because hopefully examples clarify. One thing I want to mention is that this is of course not like fixed formula to solve things. You can interchange one or two as to your liking. Maybe you identify the smaller random variable first, the sub-random variable first. That's fine too. Okay. So next example, coupon collector. And this is kind of like a nifty example, because I see this example being used in one way or another, or like there are more advanced concept that is derived from coupon collector. Okay, so they use coupon collector as the basic idea first. So coupon collector is saying like you have n types of coupon you want to collect. There are different kinds of coupon, and you draw them with replacement. Okay, you keep trying, but once you collect one type of coupon, it is returned back to like the bag, for example, the bag of items. Then you try again with some possibility that you collect the same coupon. Okay, as someone has asked just now, like what if we do it without replacement? Then after n times you try to collect the coupon, you have collected everything, right? In the case where there is no replacement. So intuitively, if you put things back into the bag, right, you draw things and potentially get back the same coupon that you already have. Intuitively, you need more than like order of n trials probably, right? But how much? How much more? That is the question that we want to analyze here. Okay, so what is the expected number of times you have to keep trying before you have at least one of each type of coupon? Okay, so for example, like I don't know if you guys use GrabPay. I do, and sometimes during the Chinese New Year they have this Zodiac coin hunt. So they have 12 different coins, right? So I always keep wondering, how many times do I need to use GrabPay before I can collect every single one of these coins? Because once I get a coin, right, I can potentially get back the same coin. So not so what. Okay, so how many times do I need before I collect all these coins? Okay, so that's another perspective maybe if the coupon is too abstract for you. It's rigged. Yeah, I think the probability is not the same. So I think coupon collector analysis cannot be used here. Yeah, so it's very rigged. Yeah, so coupon collector, let's focus on coupon collector now. So let's say all the coupon can be drawn like with uniform probability, right? Let Ti, so note here, this is how I define the random variable. And this is the pattern that I was telling you just now. Here I jump to step 2 directly. Okay, same like Google Pay. Yeah, I think one of the characters is super rare. Right. So coupon collector, right? Let Ti be the number of trials to collect the ith coupon. So what this means is that I finished collecting I-1 different coupons. I want to get the ith coupon. Okay, ith kind, for example. So this is step 2 in my pattern. Okay, so for example, here maybe I've collected 11 coins, right? I want to collect the 12th coin. I want to collect the 12th coin. So this is T12. Okay, hopefully this formalization makes sense. Now, success here for me is to collect the ith coupon, right? I managed to successfully collect it. And the probability of it, right? So remember, I want to calculate the relevant probability. I want to calculate the probability, and this thing, it maybe looks a bit scary, but if you give it a quick thought, right, what it means is that I have n things, I have n coupons, but I have chosen I-1. I have successfully collected I-1. Okay, so I don't care about them. So n minus those I-1 things that I've collected. Okay, so this is why the probability is like this. Hopefully this makes sense. Then geometric distribution, right? Remember, this is me trying until I succeed. So this is a geometric distribution, and the expectation of this Ti is 1 over the probability that we just computed. Okay, so I just take the reciprocal of them. Hopefully everyone following so far. Any questions about how the probability is formed? No? Then I will go on. So just give me a cross anytime you are not understanding. So I'll monitor the participant list. Okay, so now remember, we are interested in the total number of trials. We want to keep trying until we collect every single n coupons. Okay, so n being the total number of trials for n coupons. And if you think about it, it is actually the accumulation of you try until you get the first coupon. Okay, now I've gotten the first coupon. Then you try the second coupon. Okay, then you keep trying until you get the nth coupon. So it's the individual contribution of this T1, T2, all the way to Tn. And this is precisely what I'm trying to express in my pattern here, the sum of random variables. Anyone not understanding this line? Okay, if not, then I'll proceed. So applying expectations to both sides. Remember, we want to count the expected total number of trials. Okay, how many times the expectation? So I apply expectation to both sides. And if you see something like this, as I said before, you should feel your hand is very itchy. You want to do linearity of expectations. Okay, so you do linearity of expectations and then separate them like in this way. Okay, very nice property. Okay, and why did we do this? Oh, hang on, one slide. So here is another way you can write it. Express it in the summation notation. It's more compact, more concise, rather than you writing like this long string of characters. You just write as a summation. Okay, so by the fact from the previous slide, right, we use linearity of expectation. Okay, summation of all the individual expectations. Now remember, we have computed this as well. Expectation of Ti is precisely this thing. We computed this few slides ago. So what I do here is just substituting one to the other. Okay, the next thing I do is okay, for clarity, I just write it out by hand, everything. Okay, next thing I do is I factor them out. The n I factor out, and then times 1 over 1 plus 1 over 2 all the way to 1 over n. Hopefully this is familiar. This 1 over 1 plus 1 over 2 all the way to 1 over n. Hopefully you feel like you have seen this somewhere. Okay, and you should, because we just went through it, it's a harmonic series, but kind of like in reverse, because in the original one, right, it's n all the way to, it goes down from n to n minus 1 to 1. Here, I kind of like reversed it implicitly, okay? But this thing is exactly the harmonic series that we just learned, okay? And the harmonic series Hn is, what we care about is its theta log n, okay? So over here, theta log n. So actually, right, what we just computed, oh, I didn't have a slide for that. What we just computed is the expected number of trials is actually theta n log n. Okay, you just need a log n factor more than like n. Okay, so not so bad. Even if you have things with replacement, in expectation, it is still n log n. Any questions about this analysis? Because you will apply this analysis sometime in one of the questions later. Okay, so I'll stop here for questions if any. Give me a thumbs up, please. And if you have questions, give me a cross if you want me to re-explain.
Can you explain why the PI, right, is n minus I minus 1 over n?
Right. So you're asking about this, is it? TI. Right. So remember, how did we define TI? TI is the success. Sorry, TI is when we collected the IF coupon and we succeed collecting it for the first time. Remember, we keep trying, and we keep failing until we manage to collect the IF coupon for the first time. Okay, so the probability of that, right, is this quantity over here. And the over n is clear because we have n coupons. Hopefully, it's clear, it's over n. And the numerator is n minus I minus 1, because you can imagine, right, you're collecting the IF coupon. Or maybe let's talk about coins, right, the zodiac coins. You want the 12th zodiac coin. By the time you want the 12th zodiac coin, you would have collected 11, right? Following so far?
No.
Right? So we care only about the remaining ones. Okay, so Kevin, I'll answer your question in a bit, right? So this n minus I minus 1 is because you only care about collecting the let me see, let me try to draw. This I minus 1 is because you are excluding that 11 coins you have collected. You don't care about the probability of collecting them because success for you is collect the IF, the 12th coin. Okay, so Kevin is asking, during the collection of T1, you might collect T6 or something. Is this taken into account? Okay, so the thing is here, right? Something subtle about this analysis is when I say IF coupon. Okay, wait, my pen is not working. Oh, it's working. Yeah. So the IF coupon, right? When I say IF coupon, it's not like you are giving an ID to the coupon. Okay, so it's not like saying this is coupon 1, this is coupon 2, this is coupon 3. It's not saying that. So it's saying that it's the IF coupon that you have seen. Okay, so it's not labeling a coupon. So I think your question is more like T1, you think that it's collecting just this one guy. Okay, but what T1 means is that right now I don't have any coupon. What is the first new coupon that I see among these? Like all three of these things are candidates for T1, sorry. Okay, so this is a subtle point which I understand why people might be confused. Okay, so hopefully that clarifies. Very nice. Okay, nice, so I'll go on. If any questions, please ask in the chat again. I'm okay, happy to repeat. Okay. So hopefully you can, like Rizal can see the analysis follows from the fact that expectation of Ti is 1 over this probability. The probability we computed just now, we just take the reciprocal. Okay. Then everything is math from here on. Okay, nice. So let's go on. So question 3. This time, right, I want to ensure every single one of you participate. Okay. And again, by my funny policy, I will keep trying at random with replacement. So for example, here I have asked Naruto to answer a question. Then maybe I ask him again by my random choice. Okay, I know it is more efficient as proposed by a PM just now to just like do it without replacement. But for the purpose of question, right? Let's say you have n students, how many questions should I ask in expectation? Okay, hopefully something comes to mind immediately. It's not a trick question. Okay, it is. If you think it's easy, it is easy. The key point here is with replacement. Okay, with replacement. Okay. Yep, I think the numbers are racking up in Archipelago. Oh, sorry, I forgot to say it. Please fill in Archipelago. Okay. Okay. Nice. Okay. So I think I'll go on. Hopefully you okay. So there are actually a couple of theta n as the answer. So, but I want to mention that this is actually exactly the coupon collector problem if you think about it. Okay. This is actually exactly the coupon collector problem. Why? Because you can think of the coupon like the students as the coupon. I am trying to choose the students with replacement. Okay. So that is kind of like me wanting to get the coupon. Okay. So with this in mind, like if you try to do this mapping, this is actually coupon collector exactly. So the expected question asked is supposed to be theta n log n. So there are a couple of theta n as the answer. Well, of course, like okay, some of it was a very early answer, so I think that's fine. But for those who answer theta n, hopefully this explanation makes sense. Do you need me to go through why it's theta n log n or how to frame the problem? Okay, so I'll wait for people if they have questions about this. Okay, okay. So if not, then I'll go through the next question. Okay, next question is kind of like the pinnacle of this tutorial. It's like putting everything that you just learned today into practice. So here what happens? I have n distinct names, n of you, right? The whole class is n people. M of you are males. Okay, not everyone here are males. Okay, there are some females in our class as well. Then the thing is, right, I want Q out of the M males. For example, maybe there are 10 males in this class, and then I want to get 7 of you, for example. Q is 7, M is 10. Okay, so this algorithm that I adapted from the tutorial, right, it's exactly the same except I clean up the notation a bit. I randomly choose, right? I randomly choose from 1 to n. I randomly choose until I get Q of you, like maybe 7 of you. Okay, what do we want to do is that we want to count how many times in expectation I have to try. How many times do I access this array of names? Okay, so does this question make sense? So if it's not making sense, let me know. I'll repeat it again. So the idea here, imagine you have a class of 30 people. 30 people, 10 of you guys are males. Then I want to keep trying until I get 7 out of the 10 males. Okay, so that's the question. And the question is, how many times do you need to access this array? How many times do I need to try? So this will require a bit more math. So I'll give you a bit more time to try this question. So maybe let's try until like 4:43. It's a bit fast, but let's try. 4:43 p.m. Let's resume. Nice, very nice. So the math is a bit tricky, right? Hopefully you don't like just have it in your head. Take out pen and paper and actually try. Okay. It's fine to get it wrong. It takes some time. Okay, I see a couple of answers there. So if you're stuck, let me drop a little bit of hint. Hopefully you see that this is like similar to coupon collector. Okay, then maybe I'll put the slides back here for you to see that how you can analyze. Okay, maybe I'll give it a bit more time because a bit lacking in response. Maybe resume at 4:45. Okay. Starting to get responses. Okay. Just one more minute, maybe 1 more minute. Yep, 4:45. 1 more minute. Okay, I'll get ready. Maybe one more response if 4:44. Okay, I see a couple of answers. Some are close, but not quite, like missing some terms, but generally good attempts. So yeah, so hopefully, again, as I hinted earlier, right, it should feel very familiar. It is almost like coupon collector, but the difference with coupon collector is that we modify it to stop early once we have Q coupons. Okay, just now we want to collect every single one of N coupons. This time we stop early. Once you have a certain number of coupons, you are satisfied. Okay, so the coupon here is kind of like the male students, right? I want to collect the male students. Then the choosing coupon with replacement is basically like the algorithm accessing array A. We don't remove anything from array A, so it's with replacement. Okay. So now this is how to form the random variables. Okay. So we let X be the total number of accesses, and similar to the coupon collector example, we let Xj be the number of accesses to obtain the jth male, right? To see a new guy for the jth time, after the jth new guy. Okay, to see the jth new guy. Okay, so the difference here is that we stop at Q, stop until Q has been found. Okay, so okay, I don't know. Okay, I forgot to delete this slide. So same as before, let's try to analyze like the probability, right? So this is me going through step by step. To find the first male, right, there are M out of N people. Find the second male, we care about M minus 1 because we have gotten that first guy, right? We only care about M minus 1 guys. Then finally, the J of male is M minus J minus 1. Okay, so hopefully similar to just now, you can see that this is a geometric distribution with success probability of this thing, M minus J minus 1 over N. Okay, here I just expand the negative signs in. Okay, thus the expectation of Xj is the reciprocal right? And this must seem familiar for you by now, right? You've seen this a lot today. N over M minus J plus 1. Okay. Now let's analyze this. Okay. This slide, so the analysis is pretty long. I actually have 2 sets of slides for this. This is just the first one, so not so bad. So this is how we define X. Remember the expectation of the sum of the XJs. So math ahead. So pay attention if you are starting to doze off. Okay. So again, we have expectation of sum of random variables. You should feel itchy hand to push this expectation in by linearity of expectations. Okay. We have analyzed this to be this value over here. We have analyzed EXJ to be N over M minus J plus 1. So just substitute that. Then here is me to get ready for the main show. Okay. Expand the sums like this. Okay. First slide, not so bad. Next slide. So I just copy this from the previous slide, right? This is where the things get more interesting. Right now, all right, stop and think. You look at this. Does this seem familiar? Like, what is this M plus M minus 1 all the way down? Okay, should seem familiar. Okay, they should look like harmonic series, hopefully, to you. Okay, but the difference here is that harmonic series start from 1 over 1. So it's not exactly harmonic series, but it is close. Okay, so when you see this like decrement by 1 by 1 by 1, you should think harmonic series. Okay, see if you can apply harmonic series somehow. But we cannot exactly apply it now because it doesn't end with 1 over 1. There's this missing lower half of the harmonic series. So what should we do? Okay, so this is what we can do. We introduce more terms. Okay, this looks scary, right? Like, oh shit, more terms. Okay, but what I'm doing is actually very simple. I introduce these 2 terms that cancel off. But these 2 terms that cancel off helps me so that the first original sum will go all the way to N over 1. Okay, so it's like saying 5 plus 4 plus 3 equals to 5 plus 4 plus 3 plus 2 plus 1. Then you minus away the 2 plus 1. Okay, so I'll stop at this slide for you guys to process what just happened. So the reason we are doing this is we want to make it look like harmonic series. We want it to actually end with 1 over 1. Okay, so with this, and the nice thing about this is that we'll see in a bit, right? Okay, sorry. So I'll factor this out first. The next step is to factor out. Oh, before that, any questions? If no questions, then I'll go on. So I'll factor out the N, right? Just to make it neat, to make it really look like harmonic series here. Then exactly harmonic series, right? It starts with 1. The nice thing is that the other side, right? The other side is also yet another harmonic series. So the difference is that this harmonic series ends with M minus Q. This harmonic series ends with M. So both of them are harmonic series, but with different number of terms. So we can kind of like substitute the 2, right? Substitute the N here with M minus Q and M respectively. And then, okay, I put theta immediately because I don't want to deal with the plus O1. But hopefully you can see that this is log of M, right? And this is log of M minus Q. Okay, so I think most of you in answer I see are close, right? I see like log M and log Q, right? But if you are careful with the analysis, you notice it's actually log of M minus Q here. Okay, then just further simplification by logarithm laws, you can do log of M divided by M minus Q. So this is just further simplification. Okay, so cool. This is the expected total number of accesses given in this context. You have N students, you have M things that you want to get, and then out of that M things you get you have M things that are the candidate, and then you want Q of those M things. So this is the expected total number of accesses. Very similar to coupon collector, just a bit more math. Okay, cool. Any questions about this analysis? I'll stop here. While I stop here, I'll share this slide in the Zoom chat. Tutorial is effectively over. This is all the questions we're gonna cover. Although I do have like additional section, but I will release this as a like LaTeX note as well. So I'll share this with the cohort later as well. So it's fine if you don't want to stay, but I'll talk about this technique because Okay, sorry, I have some questions, but let me share the this to the Zoom chat first. So I received two questions, one via PM, one via public. I'll answer the first one first, which is public. Why can't we drop the last term? Okay. So I think the question is asking Wen Jin, right? It's asking why can't we drop, why can't we drop this term, this log n minus q? I think you're asking this because it says minus n log n minus q. Is that your question? So I think you can kind of like drop this last term, but then you cannot guarantee that it's theta. You can guarantee that big O, like it's upper bounding, is upper bounded by n log m. But for you to be more like precise, more tight, we want to keep this log m minus q. Does that make sense? Yep. Okay, nice. So okay, actually the PM question is exactly the same question. Why can't we further simplify it to n log m? Yeah, so we don't want to like drop this term because it allows us to give like somewhat like a tight analysis. Okay, if you just want big O, then I think it's fine. It's fine to drop this n log m minus q. Okay, great. So yeah, I shared the slides in the chat. I think should be accessible. Let me see. Yeah, people are streaming in. So very nice. So if that tutorial is officially over, it's 4:53. You can go if you want. This session is still recorded and I'll release the additional section as notes later as well. So I will just go through this for the people who are interested because I also think this is an important technique. It's simple, but it's an important technique for you to know. In fact, you see it in this week's lecture as well. Okay, so indicator random variable is a special case of a random variable. Okay, indicator random variable is kind of like a form of the counter, right? It's a counter for the occurrence of some event. It counts whether something happened or not. Okay, so we let x be an indicator random variable where a certain event occurs with probability p. We associate it with a certain event that occurs with probability p. Indicator is either 1 or 0. Okay, this 1 or 0 means that the 1 is saying that, okay, this event happened. The 0 is saying this event didn't happen. Right? We want to count how many times it happened. So we map it to 1 and 0. Okay, we count whether some event occurs or not. So the very useful property of an indicator is its expectation. Okay, this is the definition, right? It's either 1 or 0. So by definition of expectation, okay, it is 1. So the value, it takes on the value 1 with probability p. So it's 1 times p plus 0 times 1 minus p. Okay, so, and you know 0 times anything is 0, right? So this is essentially just the probability p itself. Okay, this looks very simple, right? Expectation of the indicator is the probability of the event happening. It's very simple, but it's actually helping us to calculate a lot of nifty things. Okay, because once you have the probability p, you basically get the expectation for free. You already know that it's equal to the probability. Expectation equals the probability. You don't need to do any additional calculation. Or if you want to be rigorous, maybe you want to show this also. But it's a known fact that expectation is the probability p itself. Okay, so I want to now remind you, this is the pattern I was talking about. They are interchangeable, right? You can identify what you are counting and you express it as the random variables, the sum of the random variables. So in this case, I want to express it as the sum of indicator random variables. So later on, you'll see I make x1, x2, xn. They are all indicator, okay, in the next example. Okay, let's go through an example together. Let's say we have 4 fair coins, right? And you flip them one by one. What is the expected number of hits that you get out of this like game of flipping 4 coins one by one? Okay. Intuition hopefully tells you that 2 should appear hit. Makes sense, right? You have 4 coins, probability half. Intuition tells you it's probably 2. Okay, and your intuition is not wrong, but let's formalize this intuition. Okay, so let xi be the indicator random variable for the event that coin I flips hit. So 4 coins, I say that maybe coin 2 is x2 and coin 2 is coming up hits. probability is half. Okay, so let X be the random variable for the number of hits in total you get at the end. Hopefully you can see that this is similar to the earlier coupon collector example. It is X1 plus X2 plus X3 plus X4. And the intuition here is that like the X1 here contributes to 1. This X here is the total, right? This X1 contributes either 1 or 0 for whether it happened or not. This contributes 1 or 0 whether it happened or not. If every one of them is 1, 1, 1, 1, that means all 4 of them happened. Then the left-hand side is 4. Okay, so yeah, this is the intuition. If you need me to repeat it, I can repeat it later. But just know this is how we formulate the random variable as a sum of random indicator. So expectation of X, let's analyze it now. Okay, so expectation of X equals to this thing, right? I just substitute how I define X, how I decomposed it. And then by linearity of expectation, you can separate them. Now this is the nice thing. The next thing is that we know all these expectations for free because we know the probability, right? It's just P. Okay, and because we know each of the probability is half, then it is half times 4, which is 2. Okay, so hopefully you can see like this is how we can analyze the total number of hits. Again, like you might feel like this is a bit overkill, right? Like it feels the intuition tells you it should be 2, but this seems like a lot of work just to show it's 2. But this technique, you can generalize it further. Let's say what if I have n fair coins? Okay, expected number of hits. Analysis is actually not that different. And you can repeat the same analysis, but instead of x1 plus x2 all the way to x4, or actually I can just write x3 plus x4, you generalize it to all the way to plus xn. So you should get n over 2 at the end. Okay, so hopefully you feel that this analysis, you pick up this idea of decomposing it into indicator random variables, and then you calculate their probability of success of happening, and then you get all the expectations of these all these terms and just sum them up to get n times the probability. Okay, in this case it's n times half, n over 2. Okay, so this is where I kind of like stopped for the other class earlier this week, but I realized I think I should have gone through one more example to make you feel that this analysis is actually useful. This is where your intuition might not work so well anymore. What if you have a biased coin, right? You have n biased coin, every single one of them is different probability. The first coin has probability 1 of hits. The second coin is 1 over 2. Third coin is 1 over 3 of becoming hits. Okay? Because all the probability are different, right? Your intuition doesn't exactly help as much anymore compared to before, right? So try to analyze this. Okay, try to analyze this by yourself. I think, yeah. So someone already mentioned in chat, is it log n? Yeah, it is log n. Okay. So okay, for those who are still like trying to figure out, okay, I'll give you like a minute maybe. So because tutorial has ended anyway, this is kind of like extra time anyway. So try to figure it out, okay? Or at least put it on pen and paper, you know, like writing indicator random variable, writing the random variable, the steps lah, make it muscle memory. Yeah, sure. So someone is asking if you can leave. Sure, you could have left like a few minutes ago before I started this section. So feel free to leave anytime. This session is recorded. Yeah, this extra stuff. Okay, so I'll go on with the slides. And someone has noted, so I don't have like step-by-step slide, but this is how I did the working. So we note that the expectation of xi is the probability, right? And by definition of how I design the question, it's 1 over I. So, well, expectation of this thing, right? So this is, okay, we want x equals to x1 plus x2 all the way to xn, right? Then what we do is that by linearity of expectation, we just push this expectation in, okay? After pushing the expectation in, this EXI is exactly this thing, 1 over I. So we just substitute it here, 1 over I, okay, 1 over I. And then, well, by harmonic series, which we just learned today, right? 1 plus 1 over 2 all the way to 1 over n, that means this is theta log n, which means the expected number of hits is logarithmic to the total number of coins you have. Okay, so hopefully you can appreciate a bit more like why indicator random variable is useful compared to before, where I just have like fair coin all the way. So with that, I think we can conclude the tutorial. I do have one more example, and it is also worked, right? But for those of you who went to lecture this week, hopefully this slide makes more sense now, because this proof is exactly the same idea. You have an indicator, AI, here, calculate the probability of AI, okay? So number of collisions is how they kind of like formulate the sum of random variables, sum of indicator, and then they do this analysis. Okay, so yeah, with that, I think let's conclude this tutorial now. It's already over time. It was extra session anyway. But yeah, I'm open for any questions, and I do have received 1 PM. This is unrelated and probably outdated. How do we know that we get theta? Okay, someone is asking how do we know to use theta or big O or big omega. So for just now, right? Generally, big O is fine for most cases. Although so if you can show big O, usually it's sufficient. Oops, sorry, this shows the answers already. But for this case over here, I put theta because harmonic series. Because of the harmonic series, I know exactly it's theta. Sorry, where's the harmonic series slide? Okay, damn it. I'll go to the table of contents. So I put theta because I use harmonic series here. And this is, I know that harmonic series is theta log n. Just now, that's why I put theta instead of big O. I kind of know it's theta. Is theta log n less than equals to O log n? So, okay, so let me think. Okay, so the thing is, right, the big O notation is actually a set. Like O, okay, usually you always say O, something is O1 equals O1, something is equals On. But the more accurate term should be like, it's an element of O of n, because O of n is the set of functions that all grow linearly. Okay, so that's the definition. So I hesitate to say is theta log n less than equals to O log n, but I think you probably can say something like if Fn is element of theta log n, then Fn is an element of O log n. I think this is fine because theta log n is equivalent to saying that it's O log n and big omega or log of n. So this is kind of like the definition of theta and theta. Okay, so someone is asking what if the series that we use is unknown whether it's theta or O. Then if you can provide me an upper bound, then yeah, just give me O. If you don't know whether it's theta or O, give me O first. Okay, but don't be too like don't need to be too concerned about whether it's theta or O. Okay, theta when possible, but no need to like flip the world over if you don't know what theta is. Yep, no problem.
Hi Christian, can I ask a question?
Yo.
Like, actually, I am a bit confused over when should we use which one. So like we have learned Bernoulli's trial.
Yeah.
Basically, like I think the coupon collector is also kind of geometric distribution, right?
Yeah.
And for geometric distribution, the formula for expectation is 1 over p.
Correct.
And for the one we just go through the indicator random variable, we have a different formula for the expectation.
Right. Right. Right.
Yeah.
Okay. So I understand if it can be confusing, right? So this is contextual. So in geometric series, so just now in coupon collector. So actually that's a good question, right? Because I kind of go through two examples and hopefully I don't confuse people. So in coupon collector, this is the random variable.
Yeah.
Right? It is the number of trials. So it can be 1, it can be 2, it can be 3, it can be 4, all the way to infinity, maybe. Like if you're very unlucky, you'll never ever get the coupon that you want. Right? Does that make sense so far?
Yeah. Yeah.
So this TI, right, is describing you try 1, try 2, try 3, all the way until you stop, until you success. Until like some trial, so question mark, some success. Okay.
Yep.
So some success, then this success, right? Because this is the kind of like the behavior of the random variable, like this is what we are doing to count this TI. This is a geometric distribution. Try until you succeed. Okay. So if you come across something like try until you succeed, chances are it is geometric distribution. The difference with indicator random variable is that in indicator random variable, the individual xi, right? X1 here is just coin flip, just a single coin flip, one coin flip, and that's all. In this scenario, we don't care about like trying until we succeed.
Okay.
Okay, we don't care about trying until we succeed. We just flip it once, and then call it a day. Based on that result, we deduce whether it's like x equals to xi equals to 1 or xi equals 0. Does this make sense? Does it clarify a bit?
Yeah, I think so.
Yeah, I can't exactly answer when should I use what. It really depends on context. Because coupon collector, the way we model the indicator random variable is using geometric distribution for each of the random variable. For this example here, we use indicator to kind of like count. Okay, so yeah. So okay, so I received a question over PM about week 4 assignment. So yeah, to answer your question. So that this kind of like concerns the assignment. So I can't exactly say it in recording, but to answer, yeah, I think you should trust your answer on that. But I want to mention that because the 1 over, like in case you are thinking is, the harmonic series. Like the harmonic series here, it's kind of like for finite number of terms, right? I don't know how if we can say anything when it's infinite, but I think series usually have properties, whether it's what we call convergent or divergent. So you can study whether like harmonic series is divergent or convergent. So meaning if it's convergent, the series converges to a particular value when you sum up to infinity. In your case, whether it's divergent or convergent, I think you can look it up yourself. But assuming it is divergent, then yes, that is the answer. Hopefully that answers. I know it's a bit vague because don't want to give it away in the middle of like consultations.
I understand. Can you actually I still don't really get the intuition behind the coupon collector, the n-1, i-1.
Okay, can. So I'll go through that slowly. Okay, so yeah. Okay, first of all, let's talk about the way this is framed, the TI. Okay, the TI here, is to collect the IF coupon. But the IF coupon, it's not like any particular coupon that you care about. As I mentioned just now, maybe for example, I have 5 coupons, right? For example, 1, 2, 3, 4, 5. Okay, so 1, 2, 3, 4, 5. Let's say I've collected this 2. So 1 and 2 are collected. Okay, let's make it a bit out of order. So instead of 1 and 2, let's put 1 and 5, for example. Oh, okay, never mind. So I received PM elsewhere, but not important. Okay, so basically now we want to find T3. Okay, we are interested in T3 now because we have collected 2 coupons. Okay, this T3 is not saying I want this particular coupon. It's not saying I want this particular coupon with number 3. It is not saying that. It is saying I want the third new coupon. So as long as I get any one of this, as long as I get any one of this, right? Then I'm happy. I'm Gucci. Okay, does this make sense so far? Okay. So what is the probability, the P3, right? What is the probability of getting any 3 of this? Okay, so you tell me in numbers. So I've given concrete numbers.
Like 3 out of 5.
Correct, 3 out of 5. And if we have n things, right? If we have n things, okay, let's focus with n first. You agree with me? This will be 3 over n, right?
Yeah.
So what if I have collected Ti? If I collected Ti, it is what over n?
I over n. Oh.
No. Okay, so think again.
Yeah.
So, okay, so I've collected. Let me maybe go through slowly. Okay, so let's say I haven't collected T1. What's the probability of T1? I haven't collected anything. So I'll go through. So, okay. Yeah, see ya. See you next week. Yeah. So okay, sorry. So I've not collected anything. What's T1? The probability of P1. Probability of P1.
P1 is 1 over n.
Okay, so I think this is where
like n, it's like 1.
N. 1, correct.
1.
So it's n over n. So it's actually 1. So let's say 5 first. Let's n equals to 5 for concrete numbers. What's P2? Let's say I managed to collect this guy. This guy 1. Okay?
Yeah.
What's the probability of getting the second correct coupon? Second coupon that you want.
N minus 1 over n.
Okay, Wei Xuan, give me a moment, yeah? So it's you check our Telegram group, go to the sharing folder, it should be there already actually. Yeah. Sorry, you were saying? Sorry, yeah.
N minus 1 over n.
Yeah. N minus 1 over n, correct. P3 will be?
N minus 2 over n.
Correct.
Okay,
right?
I get it.
Pi will be?
N minus I minus 1 over n.
I minus 1 over n. Okay, so does this like clarify things?
Yeah.
So I think Heinrich put the number in the chat there. The number of not collected equals to like the total minus the collected already. So this is the probability Pi, and hopefully you can see that from the probability Pi, you can easily get the expectation by taking the reciprocals.
Okay.
Okay, so okay, any other questions? Or if you don't, then I have a question for you. I mean, you can always peek the answer in the next slide, but I mean, give it a try, you know, like Any questions from anyone? So yeah, if no one's saying anything, I guess I'll go through this in like 5 minutes or something. Uh, okay, is it that okay, I received a PM, it's not exactly that. I want an exact answer here. Ah, that is correct. That is correct. But it is not all of that thing. Yes, nice, good job. I think it's correct. Let me see. Yeah, that's correct. That's correct. Yeah, that's correct. It's no all of that thing because of the negative sign. You don't say like negative n equals to like on. Negative functions are a bit funky. We don't normally talk about negative functions. Good job, good job. Okay, so I think most of you have seen this question, hopefully if you're attempting now, right? So another nicer question, something out of context is this question about 2D arrays. Looks scarier. Okay, so I want precise answer in the previous case, but I think yours, the one who just PM me your answer is there shouldn't be any log term. The answer doesn't have any log term. So someone is asking, is it true if I say I cannot say on because something? Yeah, that's true. So okay, I'll PM you because there are several PMs to me. So this is another example, a bit more tricky, but not that far off. Let me just take something real quick. Okay, I will go through this in like maybe 10 seconds. Okay, okay, so I've been seeing people, I've been seeing people give me like like answers in theta notation. So like that's particularly for this example because like I want it in asymptotic notation because it's harmonic series. But usually for other questions, we want precise like numbers. But depends on the question. So read the question carefully. So I'll be receiving answers like in theta or big O, but usually I want more precise. So yeah, so I'll go through this example now. And I think, like using indicator random variable by now should be hopefully more natural to you. Okay. If you don't want to hear me go through or you still don't want to spoil, just exit from the audio or something. Or leave the call, that's fine too. So I designed this question because more like I want you to revise a bit of math. Okay. So in particular, okay, this is the working. So I let this this is the probability, right? So expectation of the ith coin flipping heads is exactly this. Then because I have log of n bias coin, the summation goes from 1 to log of n. Okay. So summation goes from 1 to exactly log of n. Then usual technique, linearity of expectation, bring it in. Then what do we do here? What do we do here is, well, again, same trick. We replace expectation with probability. Then to make it clearer, right, I kind of like expand it in this way. There are log n terms going from 1 divided by 2 power 0 plus 1 divided by 2 power 1 and so on. Okay. So this is the series that I want you to get at this point. So this is part 1. This is testing your linearity of expectation and indicator random variable. Okay, and getting to the correct series. Part 2 of this question is to kind of like collapse what is this series exactly. Yeah, no problem. Right. So this series exactly is geometric series. Hopefully you know that this is called a geometric series by now. Okay. This is geometric series that starts with a equals to 1 because 1 divided by 1 equals to 1. Okay, a equals to 1. The common ratio is half. And the number of terms equals to log n. Okay, so it's a GP. Okay, and well, then I just plug in formula for sum of GP, which is a times 1 minus r power n divided by 1 minus r. Okay, I just substitute everything here. Can quickly verify that this is me substituting the values in. Okay, and you will get 1. So 1 comes from here. Then half power log n. And this is hopefully where your logarithm knowledge, you remember a bit of knowledge about logarithms. Log n here, you get 1 over n here. Okay. So this is just math from here on. And then from here to here, again, this is preschool math. Oh, not preschool. Junior high school or even like elementary school math, where you take half, you flip it, becomes times 2. Okay, I hope I didn't butcher the explanation, but really this is a GP. Identify the starting term, the ratio, and the power, the number of terms, sorry, and then substitute and do math. So you should get this as an answer. Funny story, I initially got a 2 times 1 minus n. Then I got super confused because it grows linearly. Like it's so huge, like it grows so fast. Then I got so confused when I was first doing this. So I didn't get this question online. I kind of like thought about this myself throughout the week. Yeah, so that's why I was like checking the answers, giving sanity checks on my own. But yeah, okay, nice. Why isn't it clearing? So the next question, okay, it's 5:28. If you wanna leave, go ahead. Anyone trying this question? I will also wait if anyone is still trying this question. Because I didn't give I didn't give the answer to this question in this slide, right? But I give the answer to this question in the sheet I'm gonna release soon. Okay. Is anyone attempting this? If you're attempting, give me a thumbs up maybe so I know to wait if you want me to go through. Okay, someone's attempting, some people are attempting. Yeah. Okay, then I'll wait. Yeah. I'll give you maybe 5 more minutes. I'll go through, then we can wrap up the consultation. Okay, so 2 people sent me their answers. The final challenge is to apply to analyze randomized quicksort. And this is way more difficult than the examples I've given. But fortunately, textbook kind of like gave the detailed analysis if you're interested. Okay, bye. This is torture. Okay, so anyway, like as in there is a reason like we are going through all these okay, not so toy lah, like going through these simpler examples. It's really to build your familiarity, to be able to analyze more difficult examples, right? So hopefully by now, like you are comfortable enough with basics of indicator random variable. The advanced examples is a game of you identifying what should the indicator random variable be, right? Then after that, what is the probability that it returns 1? Okay, what's the probability that event happening? It's a game of figuring all those things out, including randomized quicksort. Okay, so okay, I don't expect like people to be able to do this because I mean it's a textbook section anyway. I had to reread it a few times to like fully understand also, but it's still an interesting extension, right? To after all these exercises you have done. So I'll go through this in a minute's time, but since you have the answer ready, I think it's should be fine. But for the purpose of recording. And I designed this question, initially I wanted to make this M, but okay lah, not so nice. Okay, it's 5:33. So I'll go through this question, then we can wrap up the session. So if you don't want to listen to it, you can exit the call or like mute audio. So here, right, again, it's a game of first identify RV. So identify RV, IRV. IRV is indicator random variable. Here, right, they are, okay, so sorry, let me go through the question first, what it's trying to see. So I have 2D array. This is N, this is N. Every cell here, right, can be 1 or 2 or 3, all the way to N. Every cell is the same thing, right? There's no dependency of whether each cell is 1 or 2 or like it's not limited to anything from 1 to N, any of these, okay? So step 1 is to identify the IRV, and I designed the indicator random variable using 2 indexes. Xij is for ijth entry to be 1. Okay, it's because our target is to count the number of value of 1. This is how I design my indicator random variable. Someone is suggesting change the array to Sudoku array so the probability is all different. I'll think about that, and if I can come up with a question, then I'll share. Okay, anyway, going on, right? So Xij is like for example, right? This is maybe 1, 2, 3, 1, 2, 3. So X32 will be for this guy over here. Okay, so expectation of Xij is equals to the probability that is equals to 1. Okay, equals to the probability, which is either it is 1 over n because you are selecting from 1 to n. Okay, so this is 1 over n. Okay, let's keep this in mind. Then the random variable x, the total number, right, is basically counting all those n squared. Okay, wait, my pen is not working. X equals to summation, is a nested summation. J to 1 to n, I equals to 1 to n. It's nested summation. You can think of it like your nested for loops when you're programming. Okay, this is Xij. So this is going through every row, going every row, every row. Okay, so Xij, this is equals to, okay, I'll copy this, I equals to 1, n. This thing equals to 1 over n. Okay, this thing equals to 1 over n by this thing. Sorry, I should have said expectation of this thing equals to the expectation of this thing. Yeah, so I skipped some steps there, but I express it in that way. Then taking the expectation of those things, then it will become 1 over n. Then hopefully you can see that 1 over n, you repeat it n times, this is 1. Right? So this is equals to, eventually this equals to summation from j equals to 1 to n of 1, which is equals to n. So the expectation out of these n squared cells, right? You expect n of them to come up with a value 1. Yeah. So this is this question. I just want to extend it to 2D because I want to handle nested for loops or like maybe for loops that go span across 2 dimensions or something. Okay. So hopefully these simple exercises make you more confident in randomized analysis using indicator random variable, and try to look at this slide again and see whether like, okay, now I'm sure what this slide is doing. Okay. And with that, I'll get ready to close the session, but I am happy to take like maybe 1 or 2 more questions if you have. No problem. No problem, guys. No problem. Okay, nice. I will stop recording, I think. Okay, no problem.